Hello everybody, my name is Tevfik. Today I'm going to present the part number 3 of our video series, and the topic of today is the axial tension, and I'm going to cover some major elements or significant elements that impacts the tension profile of the casing or the stress profile of the casing in running during running hole or in post cemented situation or any load case that can occur in the life of the well. So before I go into the each different element, let me start with the design limit plot. So on the part number 1 of the video series, we covered the burst uniaxial burst rating, which was this line on a positive delta P on the upper side of the design limit. And on the part number 2, we covered the collapse regimes, and then that was in the bottom part of this design limit plot with a negative delta P, so the external pressure being higher. And then over here we covered the impact of the tension on the collapse rating, on the collapse D rating, let's say. And then this was, if you remember, this was completely different from the temperature duration on the yield strength of the pipe. Okay, and here the so you have the compression line and you have the tension line. Those are the performance rating of the pipe. Also here you have the compression rating of the pipe, and here you have the tension rating of the pipe, and you have the design factor. If you increase the design factor, what happens is the line will come closer to the dash line, and then this one happens the same. So your effective area where the casing is acceptable effectively reduces. Another thing to mention here is these dash lines. For example, if you need a special cold clearance pipe in a let's say if you need a all size casing 1178 or 14 inch, then what's gonna happen is usually the performance rating of the burst or the collapse rating usually same. However, your compression and the tension performance ratings are smaller in the connection compared to the pipe. So one thing to take care on that side. Okay, so let's move into the major elements. So first, I put a question mark here. What is the reason that design factor is usually higher for tension than burst or collapse, uniaxial burst or collapse design factor? So we are gonna try to answer this on the second page. So first element that I'm gonna talk about is self-weight, buoyancy, and then post-cemented tension profile, and then I will cover the bending, the shock load, and the friction in a deviated hole. So first, let's cover this. Let's look at these two schematics. So I have drawn these two rough schematic here. On the left hand side, basically casing is a running hole, and then you have inside mud and then outside mud. So you have external pressure and an internal pressure. Of course, at the bottom, you have the P and P impacting, and then on the right hand side you have a cemented condition. I put a top of cement here, so there's cement here, probably there's a spacer there, and then a mud above. Anyway, and then you have the shoe track, and the top block is basically landed over here. And then on the below, we will look at let's look at the true tension value at the shoe. So what will be the difference between true versus effective tension? What's the difference? So if I put a kind of a gauge over here to measure the strain, strain or strain gauge to measure the load that felt at that point, then that will be the true tension, right? However, if I want to look at kind of a buckling concept where I need to look at just effective tension, then I will use the effective tension. So effective tension in reality is not a real force. It's more a criteria basically decide on the buckling, if the pipe is buckling sinusoidally or helically or not, and then what can we do about it. And then I'm gonna talk about a little bit on the second page. So the true tension at the shoe is basically the minus of your external pressure times the external area. That's effectively force that's applied on the shoe on the outside. That's hydrostatic, and this hydrostatic, you remember, you will use the TVD of the corresponding MD if it's a deviated well, and on the plus you will have the internal pressure times the internal area. And if I want to look at the effective tension at the shoe area, then what it will be is if I need to convert, I will convert it with the addition of the force on the outside and then subtract the force in the inside by taking the pressure times area basic equation. So what we can draw from here is, at the shoe area, your true tension is negative almost all the time when your external pressure is higher. Of course, in the running hole case, it will be still higher, so that your true tension at the shoe is negative. However, your hydrostatics are similar. So how minus it is, it will be minus due to the difference of the outside area or the inner area. However, in the cemented case, because you have the cement on the outside, the hydrostatic difference is also higher. Therefore, the difference between these terms, the force inside and the force outside, will be higher. So you will have a lower effect. You will have a lower true tension at the shoe in the cemented case. So we talk about the effective tension. Sorry. So it's at the zero at the surface at the shoe. And if I want to calculate, let's say, the true tension at the surface, what do I need to do? So I calculated here the true tension at the shoe. I need to add the weight of the casing in the air multiplied by the TVD of the casing length. All right, same as the hydrostatic assumption. So they use the same assumptions in the TVD. And then if I want to find out, for example, an effective force, or let's say somewhere here, what do I need to do is I need to calculate the true tension at this point, and then I need to convert that true tension with adding the outer area times the outer pressure and subtracting the internal pressure times the inner area. And then according to this value, minus or positive compared to your critical buckling value, then we can decide on if it's gonna buckle or not, and then take some precautions accordingly. The next one I'm gonna talk about is the bending. Of course, in a vertical well, I'm not sure if a completely vertical well exists in the world, but you know, if you have a well with dog legs in a deviated hole, then the equivalent axial tension that will be resulting from this dog leg is basically calculated with this equation. So there's basically the outer diameter, cross-sectional area, dog legs, and then there's a conversion into the pounds. So I think this bending tension is the equivalent tension due to bending is highest at the outer wall of the pipe, and von Mises yields can be calculated both on the inner wall and the outer wall. So that's why there's a question mark of plus and minus to the tension. It's maximum at the outside, I think, and the minimum on the inner wall. So you can calculate the equivalent von Mises stress on both walls. So the other one is the shock load, right? So the shock load is basically happens due to the acceleration or deceleration when we are running the casing, and then it's, you know, setting the slips or taking the slips to running hole, and then at the next joint, I think I put a mark of take caution, because first of all, it's calculated as a constant velocity in feet per second, instantaneous velocity, and the cross-section area. First of all, this instantaneous velocity, I think there is a kind of some guidelines to use, maybe 5 feet per second, 3 to 5 to 8, but in reality, to estimate it for the full casing run, and then for to estimate the maximum shock load, it might not be 100% black and white. So I think that will depend on the company guidelines, but as a general, there's a shock load that there's a equivalent axial load because of the deceleration and acceleration of the pipe. And here the another factor is the friction in a deviated valve bore. So what happens is when you run in hole, you have some friction in the case stall as well as in the open hole. So what's gonna happen is you basically have this simple schematic where you have the block sliding down, let's say, and then you have a weight in the gravity in the direction, okay, and then you have these two vectors coming in. So that's the vector, one vector is parallel to the ground, let's say, and then one of them is basically perpendicular to the surface. So if we say an inclination of the valve, it's a very simplified version, is basically alpha. Then I would easily calculate that weight times cosine alpha is the weight basically acting, okay, weight that left, and then my side force is a perpendicular one, is the weight times sine alpha. So what does that mean in practical? If I have a vertical valve, completely vertical valve, what happens is the inclination is zero, okay, it's a vertical valve, and then weight times sine of zero is zero. So which means on a vertical valve we are not theoretically coming up with any drag or a side force or any kind of a value that we basically consume the hook load on. However, in a let's say deviated hole, let's take the most extreme case of a horizontal well. So that's 90 degree, right? So sinus 90, what is sinus 90 is 1, which means my in the horizontal section my friction related, the side force will be the highest because weight times the sinus alpha is the weight, and then you multiply that one with the friction factor. So what is that friction factor? It is kind of a case stall and open hole. It will be separate, the different friction factors, but that's how you come up with your drag force. So what force, what hook load will I be left with when I'm running the casing, let's say with a weight times cosine alpha as the weight component, then that weight left will be weight times cosine alpha minus your drag force. So of course, again, the weight is here TVD, what we discuss over here, and then your weight left will be weight times cosine alpha. That's the weight component, because some of the weight is laying on the low side, and then you subtracted your drag force. And what's the drag force? Your side force is weight times sine alpha times your friction factor, and then that will be the remaining weight. So when we take into account, when we are running in hole, we take into account of friction. What we need to take account is this value over here. So weight will be reduced by an amount approximately by weight times sine alpha times the friction factor. As I said, it's a combination of open hole or case stall. Some companies say, okay, let's use a different factors, or some companies might say, okay, let's use one friction factor for the full open hole and case stall. So it really depends on different approaches. So before we move from this page, a couple of more things to discuss here. So we talk about the running hole. So let's say we run in hole, okay, and then we basically pumped our cement, and then we have an FCP, which is basically final circulating pressure, right? That is due to the hydrostatic difference between the cement spacer and the mud to the mud, and plus some friction, right? So we have an FCP, and then we bump the plug, and then we bump the plug with the FCP plus 500 usually, and then what happens is we take the pressure up to our green cement test value, right? So at the green cement test value we pressure up, and then to maybe to some pre-agreed pressure, and then that's gonna have a axial that's gonna have a significant effect on our axial tension profile, and same as the pressure test later on. It will have an impact on the on our axial tension profile. However, because now cement is not in the green state, then you will have kind of some ballooning forces acting on it, which I'm going to speak on the second page. So let's look at this case because it's very important. So we run in all the casing, we cemented the casing, all right? We cemented the casing. There's top of cement over here, you have the spacer, and then you have the mud over here, okay? And then, so what's gonna happen is, you will calculate your internal pressure and external pressure. You will have the outer area and the inner area of your casing, and accordingly, you will work out your true tension at the shoe, all right? So that true tension at the shoe and true tension at the surface, of course, you take into account the bending, shock load depending on you, and then also the friction. You will come up with a locked-in tension profile. So for the next phases, for all the load cases, your locked-in tension profile will be the basis. All right. So that's kind of a day one of your stress profile. Okay, that's locked in, and then any other load cases in the life of the well, during the completion, or in the next hole sections, or in the subsequent hole section, let's say gas kick or a full evacuation, whichever you call, it will have a associated ballooning, and then that ballooning will be superimposed or added into this axial tension profile, and then that's how you come up with design factor ratings of the load cases in terms of axial tension. But at the moment, what we covered here is we run in all our pool. I mean, we usually cover maybe 150K as a company guideline. And then we calculate our design factor while running hole, and also during cementing or the green cement test, we come up with the design factor rating of the pipe. But until now, we could calculate the true tension at the shoe, true tension at the surface, and true tension in wherever anywhere inside the casing string by accounting all the other elements, and then come up with a design factor rating of the pipe. Okay, so let me go to the second page. We covered this one. So the important things. So we talk about the locked-in tension profile. So that was the initial stage. Now we are going to talk about two significant things that affects the tension profile, final tension profile of the casing. So first one is the temperature, and the second one is the ballooning. So temperature affects the most important thing. What we could say is, if it's for example, if the load case is a hot or cold, because on the initial condition you have an associated temperature profile. It can be undisturbed or a geothermal gradient, or you can define it. However, in a load case where you have the hot fluid pumping or cold fluid pumping, you get a kick. It's the formation fluid is coming in, so it will become hotter, or you maybe bullhead the well with a cold water. You will have a different tension or compression related to the temperature changes. And I put a note about thermal modeling. I'm not gonna cover it here, but I'm sure you will be able to find published SP papers regarding the thermal modeling. So before we proceed, because I have some items that I'm using on both things, some concepts here. So first of all, Poisson ratio. So Poisson ratio, what was it? It was basically lateral strain over longitudinal strain. So when you pull the pipe, when you pull the pipe, it will try to contract on the body, and then basically strain on the longitudinally, and then that's the ratio of it. And then here I also define a strain. What was the strain? If you remember this plot from part number 1, that was the elastic region, and then stress, that was the stress and strain, and then tangent alpha, that was the slope, that was equal to the Young's modulus, which is around what, 10 times 10 to the 6 psi for steel. So the general equation that I'm gonna use on both of them, all right, both of them is basically this general strain equation on the axial side. So Young's modulus, that's the delta change in the axial stress, and then I have the radial stress and tangential stress here change, and then I have the Poisson ratio to come back. So, and plus you can take the alpha, which is the coefficient of thermal expansion, times the delta T equal to 0. So this one, where it applies, where the strain is 0, so you have the cemented string, all right? What is assumed is, in the cemented interval, whatever you do, the ends are fixed. Therefore, no movement is allowed. So no strain is allowed. No matter how much you apply, no matter stress you apply, the strain on that cemented profile is 0. That's why no movement allowed. I put the strain is equal to 0. So this side is the Hooke's law kind of a thing, stress over strain. However, this side is the temperature related movement, and then we know that both of them together total will be 0. So here we are gonna ignore this radial and radial and tangential forces, and then we will end up, because it's small, and then let's call it no pressure changes, okay, and then we call it axial stress divided by change in axial stress divided by the Young's modulus plus the coefficient thermal expansion times the change in the temperature is equal to 0, right? So the change in the axial stress, what is gonna be equal to, simply it will be equal to coefficient of thermal expansion delta T, change in the temperature from reference temperature, which is in our case the initial conditions, which is post-cemented profile, and then we multiply that with the Young's modulus, okay, and then that's you round it up. One of them is, I think, almost 7 times 10 to the minus 6 divided by 1 Fahrenheit per 1 Fahrenheit, and then Young's modulus is 10 to the 6 times 30 psi, as I mentioned here, for steel, all right, and then you end up with this simple formula of 210 minus 210 times cross-sectional area times the delta T in pounds, all right? So when we say delta T, again, to remind, is from the reference state to the current load case, okay? So that's important, and then we multiply with cross-section to get it in pounds, otherwise this will be in psi. All right, so as we mentioned, this value could be quite large. I think if you look at some load cases of stimulation or hot case, especially for tubing or when you start producing the well, and then you basically heat all the corresponding casings behind, this value be quite high, and then can basically draw your true tension profile quite low, and then have an impact on your effective tension or stress profile as well. All right, so this the next one that I'm going to talk about is the ballooning. So is almost the very one of the most significant, the other significant elements. So one of them is temperature, and one of them is the ballooning on the basically the change in tension profile from post-cemented case or locked in tension. So here I still have the same formula on as the top. However, I assume the temperature change as zero. So the temperature related stress is zero over there. So I take this time I take the radial and the tangential forces. I don't ignore them this time. Okay, and then we basically take the sum of these two. And then we come up with this stress change in the internal pressure, change in the internal pressure times the change in the inner area minus change in the outer pressure times the outer area. So where is this coming from? In the part number 4, when we list the radial and the tangential, I think we listed the tangential stress on the day number 1. However, when we list the radial, I will show again the sum of the radial plus the tangential, 2 of the 3 principal main stresses will be equal to this one. And then we have this Poisson ratio, as you remember from top. And then what we are going to end up with is basically in PSI, we are going to end up with 2 times the Poisson ratio times the change in the internal pressure times the inner area minus change in the outer pressure times the outer area divided by the cross section, right? So we are dividing cross section to get PSI. And here I put a note saying that the change in the delta from internal pressure and the external pressure is from the reference state. What's our reference state? Is the locked in tension profile, which I have talked on the first page. All right, and then in order to get into the pounds, what we need to do is we multiply it simply by the cross section. So the cross sections, they will cancel each other, and then we end up in pounds is 2 times the Poisson ratio times the change in the internal pressure times the inner area minus a change in the outer pressure times outer area. This will give us the ballooning force, or force due to the ballooning, due to the change in the internal and the external pressure from the reference state. So where is that again coming from? That's coming back from the Hooke's law, where basically you have the stress over strain is Young's modulus, and then we take that and then reference it to the cemented interval where there is no strain, so it is zero. It's not at all over there. It's fit stance. Okay, and then let's talk about this part. I think this poorer or lower compression or tension limit for the pipe, I think was discussed on the first page. On the first page, where there's a special clearance requirement. Usually, as I mentioned, there is no difference in performance rating for burst or collapse. However, there is for compression and tension for the special clearance pipe. And what they say here is basically what we can write here to answer our the question on the first page. Why the design factor for tension is generally higher than the burst and the collapse? It is because you have all these like a ballooning force, ballooning related tension change, temperature related tension change, bending, and the shock loss and the friction. Yes, we could estimate this, but for example, the temperature change, we don't have a very exact measurement at each part of the casing, right? We do a thermal modeling. Okay, we have a production for this many days at this rate, this much water is coming from this much gas, or we pump this cold fluid, the temperature profile will be this, but again, they are all modeling. Of course, it is in your hands to validate the modeling with real-time data. There's something else. And also for example, in shock load, all right, in shock load is kind of in my opinion, someone maybe can think otherwise, but in my opinion, it's not 100% black and white or accurate. I will think, and then the bending, the dog legs, yes, but you could have micro dog legs. You take the dog leg maybe maybe you say degree per every stand 1994 feet, so that could also affect. That's why you have like for example 1.3 to 1.4 tension factor. So you basically take a big let's say step from your required, so that you can account for all these different effects, and also you might underestimate some of them, so that this 1.4 is also kind of covering those things, right? And here, what we say here is, for example, let's look at a case where I cemented my casing, and then I'm drilling the next hole section. So there's a next hole section here. So and then I have a load case of a gas kick. I'm drilling the next hole section, let's say, and then what will be the ballooning force, or what will be the tension profile of the casing? How do we calculate it? So okay. On the first page, we learned how to calculate the effective tension at the shoe, right? With the external pressure and the internal pressure using the cement column, spacer, mud, and then you have the mud inside. Maybe you have a different mud when you displace the top plug, but you calculated, you got the idea, right? So then you also accounted for any friction in the wellbore. It might be deviated. You have the you remember the side force of weight times sine alpha times the friction factor, right? And then you accounted for bending. Let's say you accounted for shock load, and then so you have the tension profile. That's locked into the place, right? Don't take the green cement test or pressure test value into this profile, because at the end of the green cement test you will basically take the pressure back, right? You will bleed off the pressure. So your locked in pressure is the cemented tension profile. And then so what happens is, let's say you are looking at a gas kick load profile. So what happens is, now you have the different internal pressure profile, right? Because of your pressure wherever you take it from, frac at shoe, full gas to surface, or next hole TD gas to surface. So you basically come up with a kind of a, taking into account compressibility, you come up with an internal pressure profile. Perfect. On an external pressure profile in your company guidelines for a burst load case, what it does, for example, for let's say it says, okay, use pore pressure across cemented interval, and then above you use mud weight, for example, or you use base of the base fluid of the mud weight. Okay, so then what you need to do is you calculate an external pressure profile, correct? And then at every depth you have this one. So at every TVD, as I mentioned on the first page, at every TVD, you come up with your internal pressure, external pressure, and then at every depth you will come up with your also the internal initial conditions, which is a cemented profile. You have the internal pressure and external pressure. So what you need to do is you take a reference state, which is initial conditions, and then you take this final state, and then you basically calculate your ballooning force, basically using this formula. So you have the 2 times Poisson ratio, and then in brackets you have the internal pressure change from the initial condition stage to the gas kick case, and then minus external pressure pressures from reference state to the gas kick. This in this part, of course, the gas kick is the final state, right? So you will need to come up with pressure differential from that gas kick to the initial condition stage. All right, and then you calculate this, and then this will give you the ballooning force. Okay, the ballooning force from the initial stage, and then also you have the temperature related forces, right, which we covered on this part. So in the kick stage, so what happens is you take a 10 barrel, 20 barrel gain, whatever, and then you will have some kind of a temperature kind of a geothermal, maybe a bit warmer than the geothermal. So that's why you will have some kind of associated maybe warming up, and then that warming up it will cause some additional compression. and then you will come up with a you will come up with a true tension. Okay, and then let's say we call it a X. So at X you still have the initial condition, internal pressure and external pressure. You still have the gas kick, internal pressure and external pressure, and you still have the initial conditions, temperature, and the gas kick final temperature. So you will basically sum everything up, and then that will give you the true tension due to this in this load case. So another question. So this does it buckle? All right. So I mentioned in my LinkedIn post that I'm gonna briefly touch the buckling, but I'm not gonna go into deeper of helical, sinusoidal buckling, critical buckling load, etc. All right. So at X, all right, at X we calculated our true tension. What we need to do, as we mentioned, we need to go back to the effective tension, right? So what we need to do to get back the effective tension again, to basically calculate the true tension. We have the true tension, and then we will add the outer pressure times the outer area, and then we will subtract the inner pressure times the inner area. So here I'm gonna go to the X, and then I'm gonna look at the gas kick, what my outer pressure is, what my inner pressure is, and then I take the balance, and then you know, of course, with the summing up with the true tension to get back the effective tension, which was fictitious force that we call it, or maybe unreal. For it's not unreal. Let's say, as I mentioned, you put a strain gauge, you measure it, that's true tension, but effective tension, no, it's not like that. So if that effective tension is minus, and then I think if it's positive still, if it's smaller than your critical buckling load, then yes, it will buckle, and then if not, it will not buckle. So on a deviated hole, because pipe is supported by the low side, okay, you have the friction, but also in a certain advantage that in a deviated hole, because the pipe is supported, the buckling limit is quite higher, because the well bore is supporting the pipe. Okay, and then so what else we can do about this one? If you have a buckling, let's say, if we are computing the results and if we're getting buckling, what can we do? So there's a couple of things you can do. As you know, in the cemented interval, we don't allow any strain, right? Or buckling is not a concern for the cemented section, well cemented section. So, which means you can bring this top of cement higher. However, of course, if you have any CD concerns, or if you don't need to do so because of the the top of the hydrocarbons, you already covered it, or you have the ECD concern, or if you have losses concern, or whatever, then that's something else. However, if you don't, then yeah, there's a one way of doing it to cover bring the cement up. Or what can be done is basically you can pull pull on the casing, so that your additional tension impacts will be applied on this point X. So what it will happen is your true tension is this one, all right, perfect, and then you will have on top of it, basically you will have your force that you apply at surface, so that basically you will cover that scenario, or you will address that buckling scenario. So again here, to go back to here, we didn't cover the thermal modeling, but is quite important, especially the temperature related. The change in the tension is very important, which induces increase in temperature induces a lot of compression, and then vice versa. So that's quite important, especially when it becomes important if you have, let's say, some casing that the connections are basically the performance ratings are lower in the compression and in the tension. Let's say 80% or 70% of this is, let's say, this is body, and then this is your connection. Then of course your temperature related effective tension, and then the ballooning is becoming very important. Okay, I think we covered all, and then here again to mention that temperature effects and the ballooning is basically impacting the life of the well from running the completion, production, all the associated cases, because you bring the completion fluid inside, then it's gonna heat up. It's gonna tend to heat up the other neighboring casings on the behind. Okay, thank you very much. See you on the next video.